Welcome to the introduction of our work Deep Homography Mixture for Single Image Rolling Shutter Correction. This work is conducted by University of Electronic Science and Technology of China and National University of Singapore, published to International Conference on Computer Vision. Speaking of the motivation, we find that most existing rolling shutter correction methods require camera intrinsics or multi-frame input. And the most representative previous single image methods focus on motion parameters for rolling shutter correction, which is not straightforward enough, and it also introduces large solution space. With the development of homography estimation, the initial homography basis method generates the homography basis from random parameters, which does not imply the real camera motion in reality scenes. The key contributions of our work are stated as follows. Firstly, we propose deep homography mixture motion model for single image rolling shutter correction, which does not need camera intrinsics or additional IMU hardware. Secondly, we introduce a pipeline that nerds the motion mapping between GS and RS. That means global shutter and rolling shutter image pair, by combining motion bases which are nerred from natural videos. We also propose a new RS Homo dataset for more challenging scenes in rolling shutter. Finally, our method achieves state-of-the-art performances when compared to previous single-frame approaches. What is homography mixture model? Homography mixture is that we divide an image into several blocks. Then each block corresponds to one homography matrix. But to maintain the continuity of different blocks, we add a Gaussian weight maps to the whole image among different scanlines of different blocks. Thus, every pixel corresponding to its location from RS to GS can be a transform of the homography mixture combined with Gaussian weights. And our new dataset of RS Homo dataset follows the CA Homo dataset. We follow the previous synthetic method, generating motion trajectory polynomial, and make the motion flow to the original image. After the transformation, we crop the output and generate the rolling shutter and global shutter image pair. Speaking of the homography basis learning, different from previous one, which generates the homography matrices from random parameters, we learn the homography basis from real natural videos. Firstly, we extract the plenty of homography matrices from consecutive frames in videos, and after that, we transform the homography matrices into homography flows. Then we concatenate and flatten the homography flows using principal component analysis to find the bases corresponding to the maximum n singular values. Thus, the correction flow can be the combination of homography bases, the weights, and the Gaussian weights. So our network is designed to predict the weights for the homography basis. This is our pipeline. We input a single image, and after the neural network outputting the basis weights, we use the nerd flow basis and the designed Gaussian weight maps to make dot product and output the correction flow map of size h by w by 2. Our loss function is like the optical flow loss function. We conduct experiments on both single frame methods and multi-frame methods. The single-frame methods comparison is conducted on synthetic dataset, and the multi-frame methods comparison is conducted on color RS dataset. It can be seen that our method outperforms all the relative single-frame methods. We also show some qualitative experiment results, both single-frame and multi-frame. We do ablation studies from 3 perspectives. First, choose different weights to combine the homography bases. Secondly, choose different number of blocks. And finally, choose different number of or type of bases. We also conduct more experiments with challenging cases like depth varying and experiments with different frame rates. There are some more results on both real and synthetic data as shown. Thank you for your listening.